Okay. So the goal, even though I'm starting 5 minutes late, is to get through the rest of the material today. And then for Wednesday, we can use that as for you guys, an optional class. To be able to come and bring questions about either of the either of the options you have for homework 4. Okay, looks like my Skyper is here. Hey. Okay. All right, and we have, well, a few people turned in homework today, not many. Hopefully more of those will be coming to me soon. Just remember, the absolute last day to get anything in is Sunday, May 10th. All right, so, okay. Now, where we left off with the QR algorithm. So, as it stands now, we have a Hessenberg reduction applied to our matrix A that we're trying to get the eigenvalues of. And then, what we're trying to do to make this iteration, the Hessenberg matrix, converge as rapidly as possible to a quasi-upper triangular matrix is the double implicit shift strategy. So the shifts are used to speed up convergence, but we're doing the shifts implicitly to avoid complex arithmetic. And we've gone through a few iterations of this algorithm to address one problem or another. And where I left off last time is we define a matrix M that is h squared minus mu1 plus mu2 h plus mu1 mu2 identity. And then we do the QR factorization of M. Z is orthogonal, R is upper triangular. And then H is overwritten with Z transpose HZ. I've been referring to this as H2 in the notes because we're doing 2 iterations at a time. Now, to refresh your memory, mu1, mu2 are the eigenvalues of the lower right 2x2 block. So last 2 rows and columns. Okay, which are likely to be complex. On the other hand, this matrix M is real. But the problem is, both of these steps in this algorithm, forming M and also computing the QR factorization, actually, no. Only the first of these steps requires order n cubed floating point operations. And we'd already done a lot of work. The reason we do this Hessenberg reduction up here, because this also takes order n cubed operations, but this is done once, so that's okay. But we'd worked with Hessenberg matrix so we could finish this part in order n squared operations, but in order to get fast convergence and get rid of complex arithmetic, we just bumped it up to order n cubed. So this is a problem that needs to be fixed. The last issue we have, so that we now have a practical QR algorithm. So we're not there yet, we're just one step away. Okay, so so we have to try to achieve this silver-red transformation without explicitly forming this matrix M, without doing this matrix-matrix multiplication. Okay, so that's where we left off last time. Now, so what are we going to do instead? So what we'll do instead is, instead of computing all of M, we just compute the first column of M. Now that's hardly going to take any time at all, because M is a second-degree polynomial of a Hessenberg matrix. So when you take a Hessenberg matrix and square it, you have two entries, non-zero entries in the first column. So when you square it, that's going to add one more non-zero entry. So you're only going to have 3 non-zero entries. So the work here is negligible. So that we can say it takes order 1 floating point operations. Okay. The next thing we do is we use a householder matrix called P naught in order to so that when we apply that householder matrix to this first column of M, we get a multiple of E1. Now, this is not going to be very expensive at all, really, because, okay, so this is going to take order, let's see, so for a household reflection, well, actually, it's not going to affect very many rows, because almost everything here is already, almost everything's already 0. We only have to 0 y and z. So this is going to take order n operations, so that's not very expensive. Now, why are we doing this? The reason is P naught is the first householder transformation that would be used in computing this QR factorization, n is equal to zr. So everything I've done on the left board, I'm starting the process, but it's not going to go all the way with it, because that would be too much expense. Okay. Now, once I have that household reflection, I'm not actually going to apply it to this first column. I know what it would do. Instead, what I'll do is I'm going to apply that transformation to H, my Hessenberg matrix. I'm trying to get the eigenvalues of. Now, because P naught doesn't affect very many rows, that's also going to take only order n operations. Also, because of this household transformation, the new matrix that we have is no longer Hessenberg. We've ruined that structure, at least just a little bit. Okay. So that sets up the next step. Is now we fix the Hessenberg structure with additional householder transformations that I'll call P1, P2, up to Pn minus 2. In order to take this matrix that we got from the last step, Hessenberg Hessenberg again. This is going to be the most expensive part. Each household reflection, again, it doesn't need to affect very many rows, so just a few rows, but it updates all of those rows. So each one of these is order n operations, so the total is order n squared. This is an acceptable level of computational expense. So now we have our matrix, I'll call it H tilde is Z tilde transpose H Z tilde, where Z tilde is P naught, the householder transformation from up here, followed by all these householder transformations. P1, P2, up to Pn minus 2. Okay. So now we're going to use this instead of Z transpose HZ. So what we've done is, the inefficient process on the left board, I've started doing it. I find the first transformation used IQR factorization. I go ahead and apply that. Now, if I were to continue with m equals dr, I would use whatever householder transformations it took to finish reducing m to upper triangular form. But at this point, I forget about what I've done on the left board. I just want to fix the Hessenberg structure. And now I'm saying that using this matrix H tilde is just as good as using the updated matrix H that I had before in my slow algorithm. Now the thing is, I have not given you any reason to believe why this should work. So what I'm going to do now is compare using this approach to the final step on the previous board, and we can see why they really are equivalent.